All right. I better turn this on. All right. Can you guys hear me now? Do we have the audio on? Is it on? Hello.
It's hard to tell. This place reverberates.
It does. Like even though you were like all the way over here from the mic, like
Yeah.
I think it's on, but I don't think it's the AV is on. So
we can hear you great. Yeah.
Yeah, and they'll be able to hear you too. I just want to make sure we have it on because it helps with the streaming and stuff. Yeah. Let me
From roll reps like 3 months.
All right, we're getting there. All right, we're on now. So thanks everybody. If you just arrived, you are at the FinTech track at the Revolution. We may be renaming this track to the Randy Abernethy track because he's up here again. He's going to be talking about Apache Thrift. So thank you very much.
Thank you. So yeah, Apache Thrift. I'm a PMC member for Apache Thrift. Big fan. Used it in a lot of different projects. I actually started doing RPC stuff pretty heavily in the 90s. And back then, a lot of the RPC technologies were really brittle. And if you needed to change an API, it was like rebuild the world, total disaster. And so when I ended up trying to build out a bunch of new stuff sometime around 2007, I think it was, 2008, I was looking for a better solution than like MSRPC or DCRPC or one of those things. And I found Thrift, and I was like, holy mackerel, like this is the holy grail. This is everything that I hated about the other RPC stuff we were using fixed. And I was really so excited. The one thing I was a little bit worried about was the serialization stuff, because for some crazy fast things that we were doing, this is all for trading systems and stuff where it needed to be really low latency. We were doing binary stuff. We were like grabbing bits out of memory, slapping them on the wire, and then picking them up and sticking them in memory on the other side. So it doesn't get much faster than that. And we were actually doing tweaky stuff to like, specially space out and design structs in memory that would work in C# and in Java and in C native code as well. But when I saw Thrift, I started playing with it, and I found that it was absolutely fast enough for most anything, and that it had this amazing set of evolution features, which really sold me. And so I've been a huge fan ever since I wrote this book, have been contributing as much as I can to Thrift ever since. But this talks about how Thrift fits into the cloud native thing. So cloud native, big push in FinTech anyway. And I kind of like this little picture because it shows you what happens to your app when you go cloud native, right? Because as Casey was mentioning in the last talk, there are 3 kind of factors that really make something cloud native, right? It's microservice oriented, it's container packaged, and then it's dynamically orchestrated, meaning the stateless app part, is going to move around a lot. And so you take your app that looks like this, and you just explode it, right? The API of this thing is the same, but now there's 5 copies of it. They're being load balanced and multiplexed and stuff. And so these guys, any one of them can talk to any one of those. You don't know. This guy maybe calls the green guy, and it's got its standard API that is implemented in 15 different elements over here, and same thing over here. So the beauty of breaking this stuff out is developer productivity, right? If you want to make developers go faster, sorry, you can't do that. They're humans, right? They operate at a certain clock speed, and they can't go any faster. What you can do is you can remove the muda, right? The waste, the Toyota way, right? Get rid of the stuff that slows them down, which is coordination overhead, right? If you have to coordinate the build and deployment of this whole massive thing, your entire app that coordinates 20 teams, that's not going to be easy. On the other hand, if this guy is your fix engine that sends orders to NASDAQ, this is your maybe your dot engine that sends orders to New York, and then this is your market data summary engine, and if this is your risk management engine, right? They're all separate pieces, each one of them a piece of the problem domain, each developer capable of deploying new versions and new features independently of the others. One of the most important things you need to make that all work is the ability to evolve these APIs without breaking the world. REST has been doing that for a long time, right? Or HTTP, JSON, whatever you want to call it, however you like to do it. You can add a route to a server and nobody cares, right? If they don't use it, they don't use it. If they want to use it, they can. You can add parameters to a REST request and nobody cares, right? I didn't supply it, so figure it out with defaults. Why can't you do that with RPC? Well, you can with Thrift. That's what it brings to the table. And so being able to do this stuff fast has a lot to do with money, which is why companies, especially financial services, like it, right? If you don't want your lunch eaten by the new guy, you have to go quick, right? You have to be able to innovate quickly. You have to be able to get ideas in the hands of your customers. And that's all about this, CI/CD, right? I've seen companies do all sorts of crazy CI stuff, and then they stop there. And who benefits, right? GitHub, I don't know, right? You've got all this amazing innovation in GitHub, but it's not in front of your customers, right? You have to have a full pipeline that drops things into a production environment that people can use. That sounds scary. Financial services firms don't like scary, right? They like stable, reliable, but they also don't want to get crushed by their competitors, and so they're being forced to move this way. And we're all of a sudden finding through statistics that it's actually better, right? Because instead of building up all this risk and then dumping it onto the system and finding out all the problems in production, you're dumping out all these little events, taking lots of little chances. And if you have a dynamic orchestration system like Kubernetes or something like that, or Mesos or what have you, if you deploy this container and it doesn't work, you can roll back. And you can also do dynamic deployments where you put the new guy out there and you only give him 5% of the traffic. And if things are ugly, you shut it back off, right? There's all these things you can do in dynamic infrastructure to make this much lower risk than lights out one big deployment types of things that you get with that monolith world. And so agile development, everything is code, GitOps, all of these things are really designed to not only allow you to innovate faster, but to reduce the risk in the process. And so time to market, right? In the innovation, that's really the big thing. So cloud native adoption, are people using this stuff? 12 billion polls on Docker Hub as of 2017. I don't know what it is now, probably 15, 18, something like that, 20. This is Stack Overflow trends. You've got all these different cluster managers. It turns out if you have 20 different cluster managers and 20 different container technologies, that's actually a bummer for developers. Because developers want to innovate. They want to build software. They don't want to learn 5 different packaging schemes and 20 different orchestrators. And so for good or bad, Kubernetes has become the thing, right? This is the Kubernetes line, and everybody else is down here, whether it's Swarm or Mesos or whatever. Kubernetes is clearly, that's one metric, right? You look at any one that you want, and you can pretty much see Kubernetes becoming emergent as the thing. And you've got some pretty big apps, right? Fairly painfully, Pokemon Go was 30,000 containers on a Kubernetes cluster. There's a lot of issues in the early phases of that, but we're glad they did it, right? Because they fixed those problems. They found all the gotchas in that first phase. Google's been running 3,000 containers a second in Borg, which is the precursor to Kubernetes, their infrastructure, and you've got 567% growth in 2017 of Kubernetes. So microservices on Kubernetes seem like an interesting, combination here, right? That's the wave you want to get on, probably. And when you go into cloud native systems, you move from this environment where your app runs on an operating system in a VM, if you're cloud-based, to this kind of environment where your app runs in a container on an OS. And that could be on a VM, or it could be in bare metal, right? But you're getting rid of all of these copies of the operating system, right? If you have 20 VMs, and each one is packaging some big monolithic app that you've got, your unit of deployment is a virtual machine, you're paying this price for every single one of those that runs on this computer. Over here, you have a single operating system. And so you get better server density, and that's cost, right, to the bottom line. And you also have better performance for the I/O, right? If this is bare metal, that OS owns the hardware, right? This is the negotiator. If you say I want to write to the disk, and you say I want to write to the disk, this guy decides who goes first. But if you're over here and you do that, this guy can't decide because he's a virtual machine. He tries to touch virtual hardware, trap into the hypervisor, and then this guy then negotiates, and that's an extra layer. And that's why I/O is slower. And that's why storage solutions that are doing tons of I/O prefer this model, right? If you use a database as a service in a cloud, they're probably running it on bare metal or some sort of solution that has a really hacked hypervisor that allows them to get straight to disk because they need the performance. They don't want their database to be slow because it has to do 2 hops. Networking, any kind of I/O where you have to talk to a device that can't be multiplexed. Now there's all this trick stuff out there where you have network cards that allow 4 different interfaces and one of them is assigned to each VM and stuff like that. But that doesn't scale that easily. It's not general purpose and simple, and so a lot of cloud vendors, either charge more for it or they don't even offer it. And so this is really a nice option, right? You go with container solution, you sort of get rid of that problem altogether. So the challenges, though, that show up in these kinds of systems are this, right? You used to have these 17 big VMs, and you run 12 of each. Now you have 1,700 microservices, and you have 60 copies of each, and they're all talking to each other. Netflix calls this microservice Death Star model, right? It looks like it. Would you like to manage that or monitor that? Not without tools, that's for sure, right? So increased pressure on networks, right? Where it used to be, I call a function. Now I have to make a network call. Yikes, if I'm a financial services firm, I'm like, well, I just went from microseconds, right, to milliseconds. That's a very serious deal. That monolith is way faster, right? You went all the way back to that monolith picture and looked at the exploded microservice. That thing's never going to be as fast. The application in microservices is never going to have the low latency of that monolith. And this is why if you talk to like high frequency traders and stuff, and you start telling them about microservices stuff, they look at you like you're crazy. Like, wow, I would never do that. You're nuts, get out of my office, right? But if you start talking to people who are building systems that scale to millions of users, consumer-facing products, things that have to be scalable beyond what a single computer can handle, well, this model has a lot to recommend it, and particularly the innovation piece of the puzzle, fast innovation, especially when you're dealing with B2C types of situations. So even B2B though. So this brings us back then to that interface, right? Okay, so we've gone to microservices, we have the speed, the innovation speed, but we're losing the actual application responsiveness by adding latency to all these communications channels. We get a little bit back by going to containers and cutting out the middleman. No more VMs if we are running on bare metal anyway, or at least fewer VMs if we're running in the cloud as well. And more clouds are offering bare metal systems, right? On Amazon, you can get bare metal instances. IBM Cloud has bare metal instances. Packet is a cloud that's just bare metal. So there's options out there if you really want crazy performance. Modern RPC is an interesting fit in this place. REST APIs are awesome. Talk more about that in a second. But RPC, if I'm in a monolith and this function over here is being called by this module over here, it's a function call, right? I can take this module and rip it out and say it's still a function call. Make a function call, get a result. Routes and query parameters and JSON, that's not part of the lingua franca of an application that is integrated into a single piece of software, right? You don't have REST APIs inside software. And if you're building things from a brownfield environment, which pretty much everybody is, especially in financial services, right? We're not creating a company from scratch if you're a giant organization. There are, of course, startups that do, but many of the projects out there are brownfield. So I've got this monolith, and I need to take the pieces of that thing that I have to innovate quickly on and rip them into microservices, and I don't want to have to reinvent the whole API of the thing. I want to take the classes and the methods that it's already got and just turn that into an RPC interface. So this was an idea that was started by Bruce Nelson in the early days of the ARPANET in 1980. It's not new, it's been around for a while. Xerox created probably the first commercial solution there, and Sun RPC in 1984, those guys at Sun's, visionary, that's still in use today. They now call it ONC+, but if you're using NFS, you're using Sun RPC. From 1984. That's pretty good legs. Corba, we can't say the same for Corba, right? That's I'll just leave it at that. DC gRPC, this was everybody who didn't want to use Sun stuff, right? IBM and Hewlett-Packard and all those created their own thing. And there was a big committee that created it, so created by committee. Microsoft jumped on the bandwagon and adopted DCRPC as their own MSRPC. So this is another survivor. If you're using Active Directory, you're using MSRPC under the covers. And then you've got all sorts of other things. But the first thing that kind of showed up in this next-gen era of service-oriented architectures was SOAP, Simple Object Access Protocol, designed for service-oriented architectures for this distributed service kind of environment, but had the downfall of being XML-based. So that kind of went out of favor, it was slow. Another problem with SOAP is that it tunnels everything through HTTP, so it's posting all the time, and you don't get the get efficiencies that you have in REST and things like that. And so kind of fell out of favor. Google in 2001 creates this really cool thing called protocol buffers. They're using REST everywhere, and they go, this is too slow. Let's be able to create things that are like these JSON objects or XML objects that we want to pass around, but let's turn it into a binary piece of data that serializes crazy fast and deserializes crazy fast and is really compact on the wire. So they create protocol buffers. You in IDL, interface definition language, describe a struct, and their engine will serialize it for you in whatever language you're using, as long as it's one of Java's or one of the Java, Python, C++ languages that Google was using at the time. Also, not open source, right? So Facebook is there, want to do, keeps an eye on stuff that Google's doing internally, says, wow, that's really cool, we need some of that, hires the guy, one of the guys on the architecture team, and says, build a cooler one for us. And he creates Apache Thrift. And Facebook then open sources it. And so Apache Thrift shows up as an open source solution for this RPC stuff. It has all the goodness of the smarts that Google had put into it, but with the backwards looking, hey, we can do a couple things different and more interesting. And we get Apache Thrift. Avro shows up as a better way to serialize data for Hadoop. They created an RPC system for it. I put it on here mostly to suggest that you take great care if you are even thinking about using Avro for RPC. Try it first, right? I don't know anybody who's using it. I'll leave it at that. Next, in 2015, Google comes out with gRPC. And somewhere in here, they open, I think Apache Thrift caused them to open source protocol buffers. They're like, whoa, hey, somebody's open sourcing an RPC system that looks a lot like protocol buffers. We better open source protocol buffers if we want to keep, a piece of the market interested in us. So protocol buffer shows up, but there's no RPC system. It's just a serialization engine, right? It doesn't have an RPC server set and things like that, like Thrift does. And it's because internally, Google's using this thing called Stubby. And really cool and everything, but wired into their stuff, and so they can't really easily open source it. They didn't open source Stubby because they have other plans. They're working hard to get HTTP2 created, right, which gives us the ability to align headers, to compress data, to have bidirectional flows, to prioritize things, all sorts of problems. Headline blocking, cleanup, all the problems with HTTP 1.1 kind of fixed in HTTP 2. And when that happens, HTTP2 standardized in 2015, they show up with gRPC. gRPC is Google's RPC platform that sits on top of HTTP2 and uses protocol buffers. It doesn't require protocol buffers, but nobody has an implementation of gRPC with anything else at the moment, and probably not a lot of motivation too, because protobuf is really nice. And so, essentially, and this is in my humble opinion, take it with a grain of salt, I'm on the PMC of Apache Thrift. There's Apache Thrift and there's gRPC protobuf. Those are the two players in this space that have a lot of momentum and a lot of adoption, and a lot of use behind it. Are there other things? There's lots of other really cool things, and in a particular niche, there may be something else that's better than either of those two for that particular marketplace. But in the broad scope of RPC, those are the things that you see. Apache Thrift inside Cassandra, inside all sorts of Hadoop stuff. gRPC baked into Kubernetes and Docker, right? So if you're in the CNCF world, you're probably going to be using gRPC, and it's a CNCF project, Cloud Native Computing Foundation, which is where Kubernetes lives. And if you are in the Apache world, you're probably going to be using Apache Thrift. Though you see people on, there's things over in the CNCF side that use Apache Thrift, and there's things over on the Apache side that use gRPC. But two big pieces of technology, both really useful. gRPC is now a CNCF project, as mentioned here, but protobuf still isn't. There's some, because it was open source so early on, there's some trademarking and things that need to get cleaned up, but probably protobuf ends up under the CNCF. Okay, so how does this RPC stuff make my life easier? How do I get to use this? Do I want to use this everywhere? And questions like that are probably best answered with some examples. Imagine you've got a monolith. This thing's written in C++. It's been in your company for like 12 years. It's rock solid, trusted code paths. You don't really want to mess with it because there's nothing to innovate there, but you want to be able to use it in other ways. Imagine that this is a dynamics, wind flow dynamics desktop application for America's Cup sailing, right? And you're trying to, look at the wind speed over the foils and also the hydrodynamics to lift the boat up and all these crazy things. And you built this really great engine, but one of the things in there is a sailing statistics. It tells you which, people, who was logistics on this boat when it won, and stuff like that, just simple things. And the people who build your website code in Node.js or PHP or whatever. And they're like, we need that. If we could put that sailing statistics on the web, it would be super awesome. Okay, well, we got to get rid of this monolithic desktop mentality, take that piece and rip it out of there and make it available to everybody. But we don't want to re-engineer it. We don't want to rewrite the wheel. We already have it done. How do I take that and turn it into a microservice? Well, it's pretty easy. In Apache Thrift, you would create a service, give it a name, and then you would specify its API using the Apache Thrift IDL. Every method gets a name and a return type. And Thrift provides collections like lists, maps, and sets. And then your parameters are going to all have types as well, which could also be collections. And you give each of them an ID. On the wire, you don't want to pass MINE underbar RATING, right? It's too much. You don't want to have to compress it either. So in Thrift, all of the parameters have an ordinal, and it's the number that gets passed on the wire. And Thrift has a compact compression serialization protocol, which requires only the number of bits that it takes to represent that number, plus 1. So 1 can be represented in 2 bits. 2 can be represented in 3. So this gives you huge, efficiency passing the parameters. Another thing that you might say is, well, why do I need a number? Can't they just be positional? No, they can't if you want to be able to evolve your interface. I want to be able to add parameters to those functions when I feel like it. And I don't want to break the world when I do. That means you need a serialization layer that can detect the parameters, know which ones it recognizes and which ones it doesn't, and have defaults for values that don't show up, right? It solves all your problems when you add that one little bit of business there. So we've now created an API for this module. We just rip it out. What do we need? We need to be able to glue the networking stuff that receives those calls to our module. Easy. With this IDL, you can use the Apache Thrift compiler to generate C++ stubs. Done. You now have your server-side stubs. Then you need an engine that will start up, control the processes and threads, and handle all the connections and call the stubs, right? The actual RPC server. No problem. Apache Thrift comes with several for C++, Java, C#, Dart, Rust, you name it, right? Scala, crazy languages, Haskell, sorry if you're a Haskell fan, but anything, right? You can pretty much find support for it in Apache Thrift. Go. So we generated the stub, we've got a wrapper, we start this thing up, there's your microservice. Now what about the client guys? You take that same IDL and generate client stubs for PHP, for Node.js, for JavaScript in the browser, for C++, for anything. And now you're good to go. You start this guy up, all you gotta do is tell that client stub what's the IP and port. And he's gonna connect and you're gonna get crazy fast RPC between 2 completely different languages. But the PHP guys are just calling functions in a native PHP object or Node.js, or whatever the case may be. And it just works. And so you've now kind of broken up the monolith, right? And it's been a pretty easy go because you had everything. All the stock stuff is already built. All you have to do is define your API, and then you generate stubs for both sides. A little bit of glue code, but not much. And so is it worth it? Should I just do REST, right? Should I bite the bullet and reinvent all these APIs in REST form, and then recode the REST style stuff on the server side and recode the REST style stuff on the client side? Well, we can start with SOAP. This is an example of a server and a client running over the local loopback on a single box. all these tests were run on the same box. And the URL for the stuff where all this was written is coming up at the end, and you can try it yourself if you want. But we basically have the client make 1 million calls and then say, how long did that take, right? The clients and the servers are written in Java. You'll get different results if you use Go, if you use C++, if you use PHP. If you have a Go client talking to a C++ server, right? This is just one example, right? There's, there's lies, there's darn lies, and there's statistics, and this is statistics. So try it yourself, but just to give you a general idea of the orders of magnitude we're talking about, so 1 million requests, 375 seconds. Not bad, really, right? Running on Tomcat 7 with HTTP and XML serialization, like you would get with SoapJax WS, kind of the standard way to do it. Now we switch to REST, you end up saving about 15%. This could be attributed to different things. Number one, what's happening under the covers here? We're saying, give me a quote for MSFT, and then we're passing back a string, the ticker, MSFT, a price, which is a double, and a quantity, which is an int, right? So we're just passing back a very simple struct, bigger structs, different numbers, right? Again, your mileage may vary. But here, with a GET request to get something, REST will actually use the GET verb. It doesn't need to serialize data to send to the server to ask it what to do. It just gets a URL and you're done, right? So this is going to not serialize on the way to the server or deserialize. So you're cutting your serialization load in half. That's probably a big piece of this. The other thing is that JSON is a little easier and faster to serialize. But this is straight up JAX RS with Jersey 2, Tomcat 7, HTTP, JSON, everything pretty much the same job. Now we switch to Apache Thrift. You can use a servlet, a Java servlet in Apache Thrift and run it on Tomcat along with everything else. So that's what we're doing here. We've got a JAX RS, Jersey 2, Tomcat 7, HTTP, JSON, right? Everything the same. Over here, Tomcat 7, HTTP, JSON, but just Apache Thrift. One of the neat things about Thrift is it has pluggable serializers, so we can actually get JSON if we want to. And now we're cutting SOAP in half and taking a huge, 30% discount on REST, performance-wise. Okay, well that's interesting, but maybe not enough motivation, right? Nicholas Beard says premature optimization is the root of all evil, right? For most situations, unless you need it, you don't want to tune stuff. But let's see how far we can go. If we switch to Thrift with TCP and JSON, right, get rid of the whole Tomcat Java, traditional stack, but still run a Java server over TCP now, and still JSON though, still serializing JSON. You can see that a huge part of the overhead is this server-based infrastructure platform. When you move to microservices, do you really want containers with Tomcat in them running 12 times on the same computer? That's not how it was meant to be. That's not what it was designed for. The cloud-native way of doing things is this orthogonal projection from the old, SOA, Tomcat kind of architectures of the Java space. And if we drag that forward with us, we're going to pay that price. All those Tomcats running on a single box isn't going to help us, just like all those OSs and those VMs isn't going to help us. Slim it down, right? Muda, get rid of the Muda. And so over here, you're at an order of magnitude or more faster, right? You're in the something like 40-second zone. And then finally, get rid of JSON and go to Compact Protocol, which is basically protobuf, right? At the end of the day, Compact Protocol compresses integers at line speed, so it takes up a little more CPU, but it's very, very fast, and it gives you maybe 30% smaller footprint on the wire than a pure binary representation, but it's way more efficient than JSON. And as you can see, you cut this down by a factor of 50% or something. So you're now down in like the 9-second zone. So 375 seconds, 9. 2 orders of magnitude. When you start talking 2 orders of magnitude, well, that's a pretty nice thing to see. The other thing is, if you're worried about latency, not only is it going to be faster than some of your other options, but it's easier to take the brownfield monolith and break off microservices that use RPC, in my experience, than to switch them to a completely different scheme for building your API, the other big option being REST. So another thing that you can see, I mentioned the languages vary, and so you also have to take into consideration like who's the client, who's the server. You have Go, which is famous for being pretty quick, and it's connecting to a Python server, and you hit 1 million requests with a single client. It's pretty fast. But as soon as you load up 4 clients, the Python server barfs, right? It's dying because it doesn't have concurrency, right? Python doesn't support parallelism. You can model concurrency, but it's only going to run 1 thread at a time through any of your code. And so it's way worse than just 4 times the blue, right? You don't want to have a Python-based, multi-threaded kind of server environment. But not so fast. If we go down here, there's an accelerated version of Python. So this is kind of like a little bit of a parallel to the ROX engine inside Cassandra, right? This is a C++ native serializer for Thrift built for Python. And you just say, I want to use the native serializers rather than the Python one, and all of a sudden you get this massive performance. 1 guy still about the same. But 4, all of a sudden, that's a big win, right? So you can still write pretty fast little microservices in Python, crazy productivity, and get decent performance. But if you want extreme, you need to start going to Go and C++ and things like that, and Rust, what have you. And so you can see here, the fastest of them all is C++ clients talking to C++ servers. But C++ clients talking to Go servers, pretty close, right? And then Go talking to Go, still in the same ballpark, same zip code. And Python talking to C++, a little bit slower, JavaScript, so on. So language is a piece of the puzzle, but the beautiful thing is that in a microservice environment, if everything's Java here, we only do Java, and then you buy the company where everything's C#, right? Or then you hire this team that is doing everything in JavaScript, or you have some new skunkworks thing and it's all being done in Rust, and you integrate that, right? Microservice-based systems tend to be polyglot. You need a solution that's polyglot, which is Rest has always been really strong about. But in the case of Thrift and gRPC, both you've got pretty good language support. So gRPC, what we have to mention gRPC. First, let me say gRPC is awesome. It's a great tool, and it's heavily integrated in Kubernetes and Docker and things like that. It's got Google behind it with a lot of money and developers. They've written great documentation. They've done a fantastic job of integrating with HTTP2. If your world is web and HTTP, sadly, as an Apache Thrift person, I would have to say maybe you should look at gRPC. But if you are building backend things that have to be the lowest possible latency, then I can tell you that Thrift is generally about 4 times faster. So this is a one-sided, right? This is just the performance. There's so many other things about choosing one of these tools, and I want you to carefully consider gRPC if you're looking at Thrift, because you should look at both for sure. For any circumstance, you should look at both. But they have their differences, right? There's some things that make gRPC a rock star. There's some things that make Apache Thrift a rock star. And I don't want to leave out REST. When we talk about REST, this is actually straight out of the PhD dissertation of Roy Fielding, right? Who invented the term REST. And so one of the things that he showed here is that these caches, where you see the $sign, are a critical part of the infrastructure. Think about this for just a second. You're in a browser here, and you're hitting this website that shows you dogs that are available for adoption. And you look up the Chihuahua, and you close your browser because your boss is walking by. Then you open it again, and you look at the Chihuahua again. It comes out of your browser cache. Apache Thrift and gRPC are going to use post, which is always going to go back to the server. Compare a REST API that pulls out of the browser cache for a GET operation versus those, and REST will crush gRPC. It will crush Apache Thrift because it's coming out of your process. You don't even go over the wire, right? You just can't compete with that if you're calling all the way back to the server. And then, what if you have a cache miss? Because now you're looking up the St. Bernard. Well, everybody who works at a company and has their machine inside that company is hitting probably a proxy server. And if anybody in your company did a GET against the Bernard, it's going to come out of the proxy cache, which means it's going over 10 gig internal networks in your company, or fast anyway, right? It doesn't have to go to the internet. Your deterministic, bouncing around of packets is a lot lower, so a lot better. So you end up getting out of a local cache. You didn't have to go out of the internet. Crazy fast again. Then cache miss, because now you're looking up the Afghan, right? Well, if anybody has ever looked up the Afghan from this app, it's in the reverse proxy. in the gateway that they have standing up in front of their system, right? Pound or whatever they're using, right? And boom, you get that from the gateway, which is probably yanking it out of a key value memory store like Memcache or maybe RocksDB or who knows what, right? And so bam, you get that data crazy fast again because no machinery had to kick into gear. No disks were touched probably. Worst case scenario, you look for a dog that you've never looked for, no one in your company's ever looked for, no one on the internet has ever looked for, and you finally hit this server, and it populates every cache along the back way, and that server will never be hit again until that cache entry expires. And if you're running this site, you can do smart things to specify when they expire. Why? Because REST has headers, and it has the body. And the headers are the metadata for the infrastructure, right? For the platforms and all the tools. That's one of the amazing things about REST. And so gRPC is an HTTP2 based protocol. So you get the headers, but you don't get all this wonderful get caching stuff because you don't use get in that environment. Apache Thrift has a T-header protocol, or T-header transport, excuse me, that you can use to set headers. So you can get header benefits and stuff like that, even at the TCP level with Thrift. But you can run Thrift over HTTP and get headers that way too. So there's different possibilities there. But again, Thrift is going to typically post all the way back if you're using HTTP. However, there's some neat things about Thrift we'll talk about in a minute, but that's one of the things about the REST API. If you're using the web, if you're going out over the internet, REST is king. And there's so many benefits. This is just some of them, right? All of the infrastructure and tooling. The HTTP protocol is really a powerful and important thing. And REST APIs don't plug into it. They are it, right? They use natively all of the verbs and the headers and things like that. So there's some pretty significant advantages to using REST outside. At RxM, we actually have this pattern we call the curiously recurring communications pattern, which is a ripoff of the C++ curiously recurring template pattern. And the idea is that people tend to use REST outside their infrastructure, and they tend to use RPC on the inside. Because ultimately, at some point, they get under pressure to break up brownfield stuff or to get fast, and they need to do something internally. But on the outside, REST is the fastest thing we could have picked anyway. And it's also native, and it's also easy for other developers to adopt. Right? I'm not saying that Thrift or gRPC isn't, but it's less, right? So everybody knows REST, right? HTTP based. So Thrift has some benefits. It can do HTTP, HTTP2, and WebSocket from the browser, and it can go all the way back to the back end. So you don't need a gateway. This is the downfall of gRPC. Actually, if you're coming from the browser, you have to have a gateway to translate the XHR type stuff into the underlying calls to gRPC backends. Maybe they'll fix that, but at the present, they just actually came out with the gateway. So, and then there's the T-header transport, so you can get header benefits even with the compact protocol and skip HTTP altogether, get the performance, and still get the benefits of infrastructure headers if you want to. So service mesh and cross-cutting concerns. The last thing I want to point out about microservices and how this is all fitting in with Apache Thrift is that there's a lot of stuff you have to do in a microservice environment. I'm doing that time. Okay, good. Okay, so a lot of things you have to do in a microservice environment that don't have anything to do with your app, and it's a hassle, right? Oh, wait, we're a financial services firm. We need we need security in depth. These things might go to the cloud, an untrusted environment. That means if I make an RPC call, that thing has to be encrypted because you're leaving the box, right? And we don't own the network; it's shared. There's crazy stuff happening there. So we want mutual TLS, right? Not only do I want you to encrypt the data for privacy, I want you to authenticate the other guy to make sure that we can trust that he's the guy that you should be talking to. So that's a lot to ask, right? Every single service I build, I'm going to have to use privacy and authentication and mutual TLS. Yikes. What about tracing? Who called who? This customer hit something and 15 different services were invoked and there's a problem. Who called who, right? Context-sensitive observability is called tracing. We need tracing. What about rate limiting, right? You don't want to overload somebody. What about load balancing and discovering services that might be in other clusters and health checks and all that sort of stuff? These are cross-cutting concerns. They affect every single microservice. You probably want to do that once and just have it solved. So there's this thing called a service mesh, which is becoming really popular. And there's a particular one that's becoming really popular amongst them, which is Istio. And it works like this. In a Kubernetes cluster or in Cloud Foundry environment or in a Mesos environment, for at least for the Envoy piece of it, you could do something like this. You can have a control plane up here, so Istio perhaps, and then you have these proxies. And what's neat is in Kubernetes, Istio will inject the proxy into your pod. The developer just builds their software like normal, right? Oblivious to the fact that all this stuff is happening for free. And Istio injects the proxy into their pod. Now, when they make a call, that proxy is going to figure out where they should be sending that traffic, and it doesn't have to be the current Kubernetes cluster. It could be a hybrid solution where it's on-prem and in the cloud. And it might say, hey, for this activity, I'm going to go to the on-prem side, or maybe into the cloud, or hey, that other cloud in a multi-cloud environment seems to be down. I'll go local, or whatever. Right? So discovery, load balancing, rate limiting, all this stuff's going to be applied, not to mention auth and TLS. Then this guy is going to send the traffic out. So again, like we talked about on the database side, when this pod starts up, there's an actual init container that's also injected. That guy immediately takes whatever resources this guy might attempt to access over a network and redirects them to the proxy. So everything's going to get wired over the local loopback to the proxy. The proxy then decides how to make its call, talks to the other proxy, which gets the auth and the TLS all sorted, and then over the local loopback, this guy calls the other service. And so the control plane is injecting policy, like, hey, you're not allowed to talk to that guy, which means you then can't, right? Amongst other things, right? And all this can be controlled, visualized at this high level. And so in an Apache Thrift environment where we just built that little microservice, we containerize it, we deploy it in Kubernetes, you can get this meshing functionality for free. And that's pretty powerful. That will work, by the way, with gRPC and with REST. And one of the things that I can say is that this is the Istio dashboard that Kiali is the new guy that they use for visualization. You can see here's a real example of an Apache Thrift test client. Okay, time up. Okay, yeah. Calling a service, which then calls a guy in the back end, and that's an example of Istio with Apache Thrift deployed into it. Definitely should add the note that you can see a high-level TCP statistics and things like that. Today, Istio doesn't understand Kubernetes or Apache Thrift traffic. It looks like TCP to it, so it gives you some really useful stuff, but it can't do things like look at the function you're calling and decide where to go. But hey, patch is welcome, right? So we're hoping to see a lot of improvement there over the months ahead, and get Apache Thrift to be smarter or get Istio to be smarter about Apache Thrift. So I'm not going to do the demo, but it's up there. There's a link at the top there. You can see the API bench has all the demo stuff in it that we talked about. And maybe I'll just wrap up real quick. Anybody after this talk interested in Thrift a bit? Okay. Let's see, the first 4 hands I saw. I give you guys a look. Yes. Sure, yeah. So I'll be on the stage, and I'll be happy to sign it if you guys want to sign it. So I think that's the end of this talk. Yeah.
All right. So just real quick, we've got about 15 minutes in between this and the next talk. So again, we've got our other tracks here. This is going to remain FinTech. Diversity, so we're probably fully into the diversity tracks over at the Emporium, and then made in Chicago at the Native. So, and again, just another reminder, if you're into key signing, you want to do an Apache key signing, that's here, 525, there is a web form at s.apache.org/sign. If you'd like to sign up and have your key signature to send to that URL, you'll be involved in the spreadsheet for the key sign. That's all. Thank you. All set. All right. How's the baby?
She's great.
She's great.
It's
Okay. Good. What's that? Yes.
My survival. I have that on the tail. That's what she's going to turn I hope I get more of the story, tech history. Exactly, right, exactly. I've seen this before, like. Yeah, okay. Yeah, you know what? I have no idea. Yeah, I had actually. What's that? Okay. Oh, yeah, it's really simple. It's just like so it's creating the action bits of read action. Yeah, and the key is that most of the numbers that you send are actually set in the 3 coordinates. It's going to be very simple. About to be 7. And then and your reason is don't want to slow down. Yeah, well, so here's the thing. So you possibly we know so we can serialize this by once. And there's a transport, there's a layout system. There's a compact protocol. And then you can add a cheese to the transport layer. So we're like 10 extra impressions that drops on the disk. It's very small. Not probably not good for our CPU, but you could create something like some meter quick or something like that. Yeah. So I've seen people do like encryption layers and transports. No, I mean you actually make it. No, I was just checking out. A lot of that. Seriously, like Parkinson's right? Okay. Yeah, so that's yeah. If you start clustering things, then lots of it's hard to yeah. So yesterday, no, so this is we know